In this series of forensic science lecture, today we are going to discuss about infrared spectrophotometry. Spectrophotometry are of various types depending upon what kind of radiation we are using as a source for them. There could be X-ray spectroscopy, there could be UV visible spectroscopy, infrared spectroscopy, microscopic spectroscopy, depending upon the source which we are using. Infrared spectrophotometry, when we talk about, it is unsurpassed as a universal technique for the identification of the class of compounds present within a specimen. Any specimen for the forensic analysis which we are using, that can be analyzed using the IR spectroscopy. Infrared spectroscopy, in the short version we call it as IR spectroscopy. For example, let's say if we consider there are certain fibers which are found on a crime scene. So, on a generic basis we can say this could be an acrylic fiber, this could be a nylon fiber, this could be a polyester fiber, or paints on a generic basis can be said as the alkyds, acrylics, urethanes, nitrocellulose, etc. But as we go in the detail of the spectral techniques, the advent of computerized spectral databases and chemometrics, this technique can now be extended to allow subgeneric discrimination of these particular samples. Whenever we are applying the infrared spectrophotometry, it could be qualitative as well as quantitative, which can determine the molecular species of all types. So, when we are talking about the electromagnetic spectrum, the electromagnetic spectrum giving the waves in the dual nature. The spectrum rises from cosmic waves to the CGX-UV IMR, where we have cosmic waves, gamma waves, X wave, ultraviolet, visible light, infrared light, microscope waves, and then the radio waves. Being the highest energy waves as the cosmic waves and with the lowest wavelength, and the last we have the radio waves with the lowest energy and the highest wavelength. So, in this spectra, when we talk about the infrared waves, they lie between the ultraviolet visible spectrum and microscopic spectrum on that side. So, the widely used region in the infrared wave is 670 to 4000 centimeter inverse. Most of the samples which we are using for forensic analysis are analyzed in the window of mid-infrared region. The near infrared region, when we talk about, it is from 4000 to 14,000 centimeter inverse. It has also found considerable use for the routine quantitative determination. So, for example, if we have any sample for which we have to determine the quality as well as the quantity, we use the Beer-Lambert's law, where we can determine the amount of the quantity of that particular sample which is being present in the specimen we are identifying. If we talk about the far infrared region, which has been for the determination of the structure of inorganic and metallic organic species. So, infrared spectroscopy, when we say, it is different from ultraviolet visible spectroscopy in the terms that we study the electronic transitions in UV visible techniques. But as I said, infrared spectroscopy, the energy is comparatively less and the wavelengths are high. It makes the vibrations in the molecule. We also call the IR spectroscopy as the vibrational spectroscopy, and it is the most versatile spectroscopy when we talk about the analysis of forensic specimens. For examples, they are being valued for drug analysis, fiber characterization, and other applications in which such identifications are very essentials. These applications of IR techniques are exclusively qualitative, but when we require the quantification of these techniques, we couple it with other spectroscopy techniques. For example, IR can be coupled with GCMS so that we can have the quantitative analysis in the cases of drug as well as fiber characterization. So, infrared spectroscopy, as we said, the infrared radiation, it interacts with the bond between atoms in the specimens takes place. As the absorption of radiation, which is causing the bonds to attain a vibrational state of higher energy. So, when the energy is taken up by the bonds in that particular molecule, there is a vibration state because of the higher energy. There could be two different type of vibrations which can occur over there. One is stretching vibrations. These stretching vibrations, as you can see, could be symmetric, that means they are in one symmetry, and they could be asymmetric, that means there is no symmetry. Another type of vibrations which is there is bending vibrations. So, in bending vibrations, we have again different four types of vibrations, where we have in plane rocking, in plane scissoring, out of plane wagging, and out of plane twisting. These are four different kind of bending vibrations. So, actually what happens whenever an IR radiation hits the atoms of the specimens which we are testing, the bonds of that particular molecule, they may either go stretching vibrations or they may either go bending vibrations, depending upon the bonds which are present in that particular molecule. So, this because of these vibrations, there is a change in dipole moment. This change in dipole moment is being recorded, and that we record as the spectra in the IR spectroscopy. When we consider different regions of the IR spectra, maybe it is the near IR region or the mid IR region or the far IR region, they are being determined on the basis of different wavelengths. So, one of such region is known as fingerprint region. Why we call a specific region as fingerprint region? Because the molecules which are being analyzed under that region provides us the fingerprint of that particular chemical substance present in the specimen. So, as we say, the vibrational state of a bond, it depends on many parameters. For example, if we talk about its strength, we are talking here about the bond strength of different molecules which are present in the chemical, the relative weights of the atom at its termini. Different bonds require different stimulation, and therefore they absorb radiation at different frequency throughout the infrared region. So, a single infrared spectrum, when we talk about, can provide a wealth of information relating to the specimens which are present in that particular molecule. So, if we are looking for example like presence of any molecule having OH bond, the vibrations occurring in the OH bond can be characterized by the spectra of that OH bond. There is a data set which also comes with the infrared spectroscopy, and that can also help in analyzing if we are comparing two different specimens. So, regions which are being divided, these regions are divided on the basis of the wavelength. The total IR region runs from about 13,000 centimeter inverse to 4,000 centimeter inverse. Now, this centimeter inverse is the unit of wave number. Whenever we are considering the spectras in IR spectroscopy, the graph always comes between the transmittance and the wave number. So, whenever we are defining the regions of IR spectroscopy, we are defining as the basis of the near IR region, mid IR region and far IR region. For the near IR region, we have around 780 nanometers to 2500 nanometers. We can also say in the terms of wave number as 12820 to 4000 centimeter inverse. The mid IR region is 4000 centimeter inverse to 400 centimeter inverse, whereas the far IR region is for 400 to 10 centimeter inverse. Talking about the mid IR region, the mid IR region is the place where most of the analysis or the most of the specimens in the forensic science, their peak occurs. Whereas the far IR region is basically to determine the structures which have same formula, but they have different structures. We call them as isomers. So, depending upon our specimen, which we have a certain knowledge by various preliminary techniques, we can analyze the specimen under the windows of the near IR region, mid IR region or far IR region. So, the regions the infrared methods most are familiar with is absorption spectroscopy spanning the mid IR region. The region just starts above the visible one and extends to approximately 3000 nanometer. So, this is the packet which is in between the visible region here and the microwaves. So, the region lies between the visible region and the microwaves region. Usually, we report them as the units of reciprocal centimeters rather than in nanometers. This is just a convention which is being used by scientists since many years. So, when we talk about the three different regions, all three regions can be exploited in forensic work, but the mid-range technique dominates, that is from 4000 to 500 centimeter inwards. Now, talking about different types of IR region or the instruments which can be covered in that. There could be three different types. One is dispersive instruments, one is non-dispersive instruments and one is FTIR systems. Firstly, we are looking into the dispersive instruments. Dispersive instruments are basically where, as we talk about a spectrophotometer, what is a general diagram of a spectrophotometer? The first we have a source, after source we have a monochromator, after that we have our sample placed and then the detector and the recorder. So, in the dispersive instruments, after the sample, we have the gratings or the prism or the monochromator in a way that the dispersion of lights take place. The non-dispersive instruments, there we have gratings where there is non-dispersion. So, what happens? What is the difference between the dispersive instruments and the FTIR systems? FTIR is basically Fourier transform infrared spectroscopy. There are two different changes compared to FTIR and dispersive instruments. In FTIR, instead of the monochromator, we have an interferometer, and along with that, whenever we are calculating through the detector, the spectra which we get is in the form of interferograms, and that interferograms are further changed into the spectra. So, these interferograms, we use a mathematical equation which is the Fourier transform mathematical equation, which is being applied to get the specified results in the case of FTIR spectroscopy. So, non-dispersive instruments, when we say, this is for basically the analysis of a gas which is at a specific wavelength. Filters are just used for the wavelength selection and an infrared absorbing gas is used in the detection system. So, let us talk about the dispersive spectrophotometers first. Basically, these instruments are much simpler than Fourier transform ones since they measure the spectrum directly. As I said, in the case of FTIR, we first have the interferograms which will be converted into the spectra, and then we apply the Fourier transform mathematical theorem to that. In the dispersive spectrometers, the IR beam from the source is directed to sample and then to a reference position inside the sample chamber. We call such instruments as double beam principle. Why double beam? Because the IR beam is split and directly at one time it is going to the sample as well as the reference. After passing the sample chamber, both beams are combined into one common path by means of a rotating chopper mirror. The beams enter the grating, monochromator, and finally they reach the detector passing through the sample. The spectrum which is recorded in real time as the ratio of the sample beam intensity to the reference beam intensity. So, whenever we are using any sample for the analysis in the dispersive spectrophotometers, we are taking care of our sample we are taking care of our reference. Whatever reference you are using for preparation of your sample. For example, normally for the solid sample preparation, we use KBr palettes, where our sample is mixed with KBr, that is an alkali halide. So, whenever we are measuring the sample beam and the reference beam, we will first measure the pure neat KBr as the reference and then the sample. So, whatever the reference intensity will become, that is the I naught, and the sample intensity which will be I, we can reduce I minus I naught to get the exact sample from which the reference will be detected, or it will be minus through it. So, let us say a simplified diagram of a double beam infrared spectrophotometer. This is a modern dispersive IR spectrophotometer, and they are invariably double beam instruments. Why they are called double beam instruments? As you can see in the block diagram, that from the light source there are two rays coming. One is going to the reference and other is going to the sample. So, at a single point of time, two beams are passing through two different samples, in which we have placed one reference and one sample. After that, it is passing to the photometer and then the monochromator, and further the detector is there which will detect all the radiations, and we can get a spectra through which we can analyze our sample. This double beam instrument is efficiently very high, and it allows single beam operation via a Farad panel switch. So, if we are using a double beam infrared spectrophotometer, we can anytime change it to a single beam operation using a simple panel switch. So, these dispersive spectrophotometers, their most common source is MIR. What is MIR? Mid-range infrared regions. These spectrophotometers, they use a glowing ceramic bar which is called a glow bar, or we can also call it as a glober. This glober is a source for IR radiation. More intense emission is provided by the Nernst glower due to its higher operation temperature, whereas a thermocouple or a thermopile is commonly used as detectors in the case of dispersive spectrophotometers. The response behavior of such detectors is slow, which prevents rapid scanning by dispersive mid-IR spectrophotometers. So, in the dispersive spectrophotometers, or normally in the IR spectrophotometers, there could be many sources which we use, and there could be many different types of detectors which we can use depending upon what kind of sample we have to analyze. Now, the question is, if we are analyzing the sample, how do we know that which kind of sample is this? So, basically all the spectrophotometries, they are one of the technique which are used at the end after the preliminary techniques. These are the confirmatory techniques. So, when you have analyzed your sample using the preliminary techniques, you have the slightest idea using various tests, various microscopy tests or various spot tests, so that you can use it for the confirmatory techniques. These are the certain example of various sources which we can use for IR radiation. The one is the Nernst glower, which is a heated rare earth oxide rod which has temperature of around 1500 Kelvin. It gives region, IR region into 1 to 50 micrometer. Then we have globar, which is basically a heated silicon carbide rod. The temperature reaches similar to like 1500 K, and the region is mid to far IR region. We have W filament lamp, where it is being heated to 1100 K, and the radiations which is given by this filament lamp is in the range of near IR, that is around 0.78 to 2.5 micrometers. The mercury arc lamp, it is the use as plasma, and the far IR region is the range. Then we have carbon dioxide laser, which gives stimulated emission lines, and the range is around 9 to 11 micrometers. So, these are certain sources which are used for the IR radiation as a source of IR radiation. Now, there are certain detectors commonly used for IR radiation, IR spectroscopy, thermocouple, which is the thermoelectric effect which has a dissimilar metal junction, bolometer, where we have nickel platinum resistance thermometer, and when various bolometers are placed in a line, we call it as a thermistor. Pyroelectric detector, triglycine sulfate, piezoelectric material we use for pyroelectric, and photoconducting, where we have lead sulfide, cadmium sulfide, so lead selenium, this light sensitive cells, they can be used for the detection also. So, if we are imagining a block diagram, coming to the source which we have discussed, depending upon the type of instrument, whether dispersive, whether FTIR, whether non-dispersive, we use our monochromators based on that. Then we have our sample preparation we will be talking about, how if we have solid sample, liquid sample, gas sample, how that is being analyzed, and after that we have various kind of detectors. These different kind of detectors can be used in IR spectroscopy, and further then we have the recorder through which we can identify various spectra will be there to know the sample preparation. So, then we have the reflection gratings in that, and the mirrors are used which can be used to collimate the IR radiation. Various kind of reflection gratings can be used to reduce the effect of overlapping orders and stray radiations for the same. Also, when we are putting our sample, we are using the sample cells to permit various compartment which are transparent to IR over the wavelength region and inert to the various chemicals analyzed. So, depending upon what kind of sample we have, encountered from the crime scene, we can prepare the sample accordingly and we can analyze in under IR spectroscopy, and the spectra which is being given by the infrared spectroscopy is the fingerprint spectra, and we can analyze and get to know what is the chemical composition of the sample which is found at the crime scene. Thus, IR spectroscopy is one of the versatile technique which is best used in forensic science. Thank you.